In this video, we're going to continue our discussion of Taylor and Maclaurin series. The question here is, given the Maclaurin series of f of x is equal to cosine x, as cosine x is equal to summation n equals 0 to infinity, negative 1 to the power of n times x to the power of 2n divided by 2n factorial, we would like to find the Maclaurin series of g of x is equal to sine squared x. And we're given a hint, apply the trig identity, sine squared x is equal to 1/2 times 1 minus cosine 2x. So our strategy is to start with the Maclaurin series of f of x is equal to cosine x and build up the Maclaurin series of g of x is equal to sine squared x. So we're going to use this trig identity, sine squared x is equal to 1/2 times 1 minus cosine of 2x. We will apply this trig identity to find the Maclaurin series of sine squared x. Alright, starting with sine squared x, we have sine squared x, trig identity. This is equal to 1/2 times 1 minus cosine of 2x. Let's multiply the 1/2 through. We get 1/2 minus 1/2 cosine of 2x. Now, we know the Maclaurin series of cosine x. That's equal to summation n equals 0 to infinity minus 1 to the power of n, and we have even powers of x, that's easy to remember, x to the power of 2n, divided by 2n factorial. Now let's plug in 2x for x, so plug in 2x for x, because we would like to build up the Maclaurin series of cosine 2x. So cosine 2x is equal to summation n equals 0 to infinity minus 1 to the power of n, 2x to the power of 2n, divided by 2n factorial. Let's do a bit of algebra, and we get summation n equals 0 to infinity minus 1 to the power of n, and we can write 2x to the power of 2n, we can write this as 2 to the power of 2n times x to the power of 2n, all divided by 2n factorial. Now let's apply the trig identity. We have 1/2 minus 1/2 cosine of 2x, and this is equal to sine squared x, for which we would like to find its Maclaurin series. So this is equal to 1/2. I'll leave the minus outside, but multiply this 1/2 through. Summation n equals 0 to infinity minus 1 to the power of n, 2 to the power of 2n, divide by 2, times x to the power of 2n, divided by 2n factorial. Now, this negative multiplies by negative 1 to the power of n, and we get minus 1 to the power of n plus 1. So we can rewrite this as 1/2 plus summation n equals 0 to infinity minus 1 to the power of n plus 1 times 2 to the power of 2n minus 1. Because we have the same base, we subtract off the exponents. 2 to the power of 2n divided by 2, that's the same as 2 to the power of 2n minus 1, times x to the power of 2n divided by 2n factorial. Just to review the algebra once more, we have negative 1 times negative 1 to the power of n. That gives us negative 1 to the power of n plus 1, because we have the same base, we add up the exponents. Similarly, when we have 2 to the power of 2n, so 2 to the power of 2n divided by 2 to the power of 1, the same base, the base is 2, subtract off the exponents, we get 2 to the power of 2n minus 1. All right, so what we have is we have the Maclaurin series. We've developed the Maclaurin series of sine squared x, which is 1/2 minus 1/2 cosine of 2x. This is sine squared x. And we found the Maclaurin series of sine squared x as 1/2 plus summation n equals 0 to infinity minus 1 to the power of n plus 1, 2 to the power of 2n minus 1, x to the power of 2n, all divided by 2n factorial. But we would like to simplify this a little bit more. So let's expand this summation. So if we expand, we get 1/2 plus, plug in n equals 0 into the summation, we get -1 to the power of 1, 2 to the power of -1, x to the power of 0, divided by 0 factorial. 0 factorial is just equal to 1. Now plug n equals 1 into the summation. We get 2 to the power of 1, x squared, divided by 2 factorial. Now plug in n equals 2. So we get 2 cubed minus 2 cubed, x to the power of 4, divided by 4 factorial. The reason we get a minus is because we have -1 raised to the power of n plus 1, and n is equal to 2, so we get -1 to the power of 3, and -1 raised to an odd power is negative. Now, if we simplify, you will notice we get 1/2 minus 1/2, because we have -1 to the power of 1, that's -1, and 2 to the minus 1 is 1 over 2, x to the power of 0 is equal to 1, and 0 factorial is just 1. Plus 2 to the 1, x squared, divided by 2 factorial, minus 2 cubed, x to the power of 4, divided by 4 factorial, and so on. But notice the 1/2 cancels out. 1/2 minus 1/2 cancels. So let's start the index at n equals 1, because the first term of the summation, which is -1/2, cancels out. So we can write the Maclaurin series of sine squared x as summation n equals 1 to infinity, -1 to the power of n plus 1 times 2 to the power of 2n minus 1, x to the power of 2n, divided by 2n factorial. So notice that sine squared x is the trig identity. Sine squared x is equal to 1/2 minus 1/2 cosine of 2x. So we use this trig identity to develop the Maclaurin series of sine squared x by knowing the Maclaurin series of cosine x, and then building up the Maclaurin series of sine squared x based on Maclaurin series of cosine x. All right, so we have sine squared x is equal to summation n equals 1 to infinity, -1 to the power of n plus 1, times 2 to the power of 2n minus 1, times x to the power of 2n, divided by 2n factorial. And I'll review this again. We have found the Maclaurin series of sine squared x by applying a trig identity and writing sine squared x equal to 1/2 times 1 minus cosine of 2x, and we use the Maclaurin series of cosine x as a building block for developing the Maclaurin series of sine squared x. All right. Thanks.